Okay, so now we will talk about the dissociation of weak acids and bases. And what we mean by the dissociation in weak acids and bases is that if we have a weak acid, for instance, we have acetic acid. So this acid in the solution, if it's diluted in water, it will it's not a reaction, it's a dissociation, which means that it breaks into into its original ions. So it's gonna be converted into CH3COO negative and H3O positive. It should be an H positive, but H positive reacts with water to give hydronium ion, which is H3O positive. So this is the case in case of or for weak acids, and this is what we call it. It's not called ionization. For sodium chloride, for instance, it's gonna break into sodium and chlorine ions. This is called ionization. But in case of weak acids, it's called dissociation. And dissociation is a reversible process. So you have acetic acid or the weak acid reacting with water or dissolving in water to give the ions, and the ions are reacting together to give back the acid and water. So it's a reversible reaction. For simplicity and to make life easier, instead of writing like big acid like this, and to make it a more general form of writing the equations, we will express the acid as HA, where the H is the hydrogen ion atom, and the A is the acid radical itself. And in this case, the reaction would be HA plus water. It's gonna give H3O plus A minus. And this is the general form, if we want to say that. This is the general form of dissociation in case of weak acids. We can apply the law of mass action since this is a reversible dissociation, and in this case the K, we will call it Ka because it's an acid equilibrium constant, and it's going to be the concentration of products, which is the concentration of A minus multiplied by the concentration of H3O plus divided by the concentrations of the reactants, which is going to be the concentration of HA. And there is no concentration for water actually, because we are dissolving everything in water, so there is no meaning of putting water in there. So this is the form of the equilibrium or the law of mass action for this case. Let's say that I'm gonna write the equation again. HA plus water is gonna give H3O positive plus A minus, and let's say that I started with 1 mole. Let's put it like that. I have 1 gram mole of HA that is dissociating in water, and in this case, or that I'm starting with. Let's call this the starting concentrations or the flow rates or whatever. So I'm starting with 1 mole, and the dissociating. Of course, I'm not gonna have full dissociation because I must have some acid present in the solution. The amount of acid will be dependent on the value of K, but at the end of the day, I will have both of them. So I'm gonna have some dissociation for amount of X of the or X moles of the acid, which is gonna dissociate with X moles of water. I knew that because of the balance of the equation. I have 1 to 1 to 1 to 1, and this is going to produce X and X. So the resultant will be 1 minus X moles of water, X moles, and X moles. So this is the total product out of the dissociation of the acid in water. So if we consider these as number of moles, then the concentration will be the number of moles divided by the volume. So the concentration of HA, the final concentration, is going to be the number of moles divided by the volume. The concentration of the hydronium ion is going to be X divided by the volume, which is the same as the concentration of A minus. So this is what we will get out of this dissociation. And if we substitute with these values in here in the K equation, then the K would take the shape of X squared divided by V squared divided by 1 minus X divided by V, which is gonna be X squared divided by 1 minus X, and this is multiplied by 1 over V. This is the shape that we are gonna end up with for the K. That's okay, and this is nice, but we can get it more in a more general form. We already start, or the initial concentration of the acid in the solution was 1, so I can call what I can call CMA, which is the initial concentration of the acid in the solution, is 1 over V. This is 1, the initial concentration. So I can consider 1 over V is the CMA. And this is what we're gonna do, and this is gonna be the last thing. So the K would be 1 over V is CMA multiplied by X squared divided by 1 minus X, and this is kind of a very handy and useful relation, and what we call the Ostwald's rule. What we can see here, it is the Ostwald's rule, and this is a very useful rule that we can use to get the percent dissociation. And you can consider the X as the percent of dissociation in of acid in a solution. We can simplify it more by doing one more step. So let's say we have a very weak acid, and in a case of a very weak acid, the X would be very small, smaller than 1. And this is in the case of X is very small. And so X is going to be very small, so let's go back to the law of mass action. If X is small, then the concentrations of the products is going to be very small, so the K will be very small. So this is how you can think about it. So if K is small, then we can take another look at this equation here. So we can say that 1 minus X almost equals to 1. So if X is 10 to the minus 2, then 1 minus X is 0.99, which is almost 1. So it is going to be almost the same. So in this case, I can ignore this X in the denominator, but of course I cannot ignore the 1 in the numerator because I'm ignoring this compared to the 1. So in this case, K will take more simpler shape, which is X squared CMA. And from this you can know how much or what's the percent dissociation, which is gonna be X square root of K divided by CMA. So this is a simple way of predicting or calculating the percent of dissociation of the acid in a solution, only using the dissociation or the constant, which is Ka, as we mentioned before, the equilibrium constant, and the CMA, which is the initial concentration. And actually the Ka is not an equilibrium constant. For Ka we call it the acid dissociation constant. Okay. And we have here some typical values of it, like for instance it is 3.2 multiplied by 10 to the minus 8 for hypochloric acid, hypochlorous acid, and for benzoic acid it is 6.4 times 10 to the minus 5. So it's a pretty small value actually, so it's not big. And this confirms the assumption that we mentioned in the beginning, that we can ignore the X in the denominator compared to the X in the numerator. So here we have the acid dissociation constant, and we can do the same for base. For if we have a weak base, we can do the same. The only difference is that the base is gonna look like MOH, and it is gonna break into M plus and OH minus, and you can apply the same process or the same procedure for predicting the equilibrium constant, or how the K will look like, and then we will have KB. It's the same. Otto's rule is gonna be CMB multiplied by x squared divided by 1 minus x, which can be simplified, and you can ignore the x in the denominator, and we'll reach the x equals square root kb divided by cmb. So this is the same Otto's rules applies for weak acids and weak bases. For strong acids and strong bases, this is called the base dissociation constant, and this is called the acid dissociation constant. So this is all for this video, and we will continue in the next video, inshallah. I'll see you then. Goodbye.